Refrigeration cycles are found in many places. For example, the air conditioning of your automobile or your home. Also freezers, refrigerators. It's meant to be able to expel heat from volume and be able to keep it colder than surrounding temperatures. So we're going to go over a tutorial today, be able to calculate, do some of the calculations for refrigeration cycles in designing these. Now, if you haven't done so already, there's a little icon in this upper right hand corner. If you click it, you can subscribe to the APMonitor channel. Okay, so just a couple definitions. Isothermal, constant temperature. Isochoric is a constant volume. Adiabatic means no heat is exchanged. So we also say well insulated. Okay, so isentropic means that the entropy doesn't change. S is the symbol we use for entropy. Isobaric, that is pressure does not change. And then isotropic is no change with direction. Okay, so a lot of isos there, meaning the same. And then the thing that comes after it is what is being held constant. Okay, so steam. Now this is a pressure enthalpy diagram. Okay, now this particular one comes from Babcock and Wilcox Company. This is for water. Now this one might be important for, for example, the turbines that are driven by steam, for example. So what we want to do is identify a couple things in this. For example, the first one is a two-phase envelope. Okay, so we're going to. This is the two-phase envelope. So here is our saturated water, and then there is saturated steam, and then right up at the top is the critical point. Okay, above this line, okay, so this is going to be supercritical fluid. Okay, so let's draw now the 500K isotherm. So here is 600, here is 550, there's 450. Okay, so right there is the 500. Okay, so if we keep it at 500, but then we change the pressure, then we want to track and see what happens. Okay, so as we lower the pressure, it's going to make it down to where it's going to start boiling. It's going to boil, and then we continue lowering the pressure, and the volume, the specific volume, you can see that right here, is going to decrease, or actually increase, meters cubed per kilogram. Okay, so now we want to draw the line of constant 50% quality steam. So quality steam means the mass fraction of vapor versus liquid. And the quality, if you have 100% quality, it's 100% vapor. So here we can see the quality percent, and right there is 50, 60, 70, all the way up to 100, where this is the saturated steam. There's the saturated water. Okay, so there's our 50% quality steam. And then how many things can we say about a steam water system at 0.2? Okay, so that's 0.2 megapascals and 400 Kelvin. Okay, so I'm gonna track this 400 line. Okay, and if we track the 400 line, that's going to come right here and then continue down. So we're going to be right at this point. Okay, that's 0.2 megapascals and 400 Kelvin. So it's going to be saturated steam, and 100%. It's going to be 100% vapor. Okay, and we can also draw this line down and get our enthalpy. So that's 2,600, about 2,600 kilojoules per kilogram. Okay, volume. There's our volume. It's about right here if I follow the constant volume line. Okay, so that's going to be 0.9 meters cubed per kilogram. Okay, and it's above the dew point. Here's the the dew point. Dew point and the bubble point are the same. Temperatures, okay, like here at 500, there's the bubble point, 500, there's the dew point. Okay, so same temperature, but it's above the dew point or bubble point for water. Okay, and then the last thing is entropy. So this is a constant entropic line, and that is 7.2. So I'm just going to erase some of these lines here just so we can see it just a little bit better. But here is the entropy, 8.5, 9, 9.5. And so we want to try to find, there's 7. Okay, and let's see if we can find this line. Looks like it's kind of covered up, but it's 7.5, about right there. So it's going to be about 7.2 because it's between 7 and 7.5. Okay, so that's the entropy. And we're going to use that when we compress, especially for reversible compressors. Okay, so and what about 0.2 megapascals, so the same pressure, but 50% quality steam. So I'm going to draw, there's my 50% intersecting with the 0.2. Again, I can get the entropy, or sorry, the enthalpy. Okay, so the enthalpy is 1600 kilojoules per kilogram. The volume, the specific volume is 0.45. Okay, it's going to be two-phase, and then the entropy is going to be 4.4. Okay, so here's the entropy lines right there. Okay, so 4, 4.5, 5 is kind of hidden here. Here's 5.5. Okay, so we'd be able to get the entropy as well. Okay, and then we can also say temperature is 395. Okay, so there's 400, there's 350. Right over here is going to be 395 Kelvin. Okay, so that's an example of a pressure enthalpy diagram, and we're going to use this now as an example. Now this is water, okay, but we're going to use this in the next example with a refrigeration cycle. Okay, now we're going to use refrigerant 22. Refrigerant 22 is actually a hydrochlorofluorocarbon. Okay, and it is chlorodifluoromethane. Now this depletes the ozone. It's been phased out in developed countries, but it is increasing in developing countries quite rapidly, to the point that the decrease in developed countries is more than overcome by the increase in developing countries, so the worldwide production and use of it is going up. So other refrigerants, we also have, for example, R290, that's propane, much better for the ozone layer, and then also R134A. Okay, so this same analysis could be used with those as well. We just have to have a different chart for our analysis. Okay, and R134A, a lot of them are being converted to this. This is pentafluoroethane. Okay, so better for the ozone. Okay, but let's go ahead and just design this with refrigerant 22. We have 4 things in a refrigeration cycle. I'm just going to start with fluid. This is liquid at 80 degrees Fahrenheit. And what we do is we send it through, this is going to be high pressure. Okay, that's going to be high pressure. And then we're going to send it through a valve here, just an expander, an adiabatic expansion. And that is going to go down to 30 psi. So this is the lower pressure side right here. If I just drew a line right here, this is an expander. That's a compressor that increases the pressure. Okay, so and then it stays at 30 psi here. Now the 4 and the 1. Okay, so 4 and 1, those are going to be the same pressure. Okay, and 2 and 3, those are going to be the same pressure as well. But in between those, we have, between 1 and 4, we have a condenser. Okay, something that this is going to be a vapor. Okay, and then we're going to cool it down to a saturated liquid. Okay, so it's going to condense this vapor into liquid. Now on the bottom side, this is where we have, let's say we have a warm home or a warm car and we want to cool it off. We're going to boil. Okay, so this is going to be liquid plus vapor, but we're going to boil it, okay, at a very low temperature, and that's going to extract the heat from our home or automobile, okay, and turn it into saturated vapor, which then we're going to compress. Okay, so this is a refrigeration cycle. These four different streams, okay, with different temperatures and pressures and enthalpies. But what we want to do first of all is just calculate the temperature and pressure of each stream, also the enthalpies of each stream. Okay, and then we'll also get the mass flow rate of how this is, how much is cycling around. We'll also get the work that we have to put into the fluid, okay, in order to be able to compress it, and then also how much we need to remove here with the condenser. Now we're given that we need to cool this, have 5 tons of cooling, which equals 60,000 BTUs per hour. Now a ton of cooling, it kind of goes back, historically, a ton of cooling is how much refrigeration you would need to make 1 ton of ice, okay, in per day. So that 1 ton of cooling means that you can make a ton of ice in 1 day. So if you have times 5, then that means you'd be making 5 tons of ice, and that is equivalent to an energy rate. If you distributed that energy consumption out over the day, it'd be 60,000 BTUs per hour. Now typical homes, a typical home is it's going to be 1 to 5 tons of cooling. Okay, so a typical home, if you had the air conditioner hooked up to make ice, you can make 1 to 5 tons of ice per day. Okay, so that's just the overview. I'm going to go to where we can see the chart. Okay, we want to be able to look at the chart, the pressure enthalpy chart for this system. And okay, so let me come over here, and okay, so we have the same system. Now first of all, what we want to do is just calculate the properties of each stream. Okay, so let's just start with number 1. We know we're saturated liquid at 80 degrees Fahrenheit. So this is the chart that's enthalpy versus pressure. And let me just point out a couple things that are interesting about this. Here's the pressure in PSI. Here's enthalpy in BTUs per pound. And then we have a constant entropy here. Okay, so there's the entropy right there. And then we have saturated vapor, saturated liquid, and then there's like 50% quality, so 50% weight percent vapor or liquid. Okay, and then we have some temperatures right here as well. Okay, those are going to be temperatures in degrees Fahrenheit. Okay, so this is going to be the place where it's going to boil, let's say, and then become all saturated vapor. Okay, so let's go ahead and do these calculations, figure out where we are on this chart with stream 1. Okay, so that's 80 degrees Fahrenheit. So here are my temperatures. Here's the saturated liquid on this side. And so 80 degrees is going to be right here on the chart. Okay, and what we want to do is try to find the pressure. Okay, so we need to get the pressure and then also the enthalpy at that point. So 80 degrees saturated, I'm just going to come over here, and that is going to be about 170 psia. Okay, so pretty high pressure. And then if I come down here, okay, that means there's my enthalpy, and that is about 32 BTUs per pound mass. Okay, so that's a specific enthalpy. Okay, so now what we're going to do is we're going to send it through this adiabatic expansion, and let's first of all just go ahead and write our energy balance. Okay, this is an energy balance for open systems. Okay, energy balance delta H plus delta E. Okay, kinetic energy change, potential energy change is going to equal Q minus shaft work. Okay, so in this system, we're not going to consider the velocity of the fluid is going to be pretty low in comparison to the other energies, and the potential energy, let's say there's an elevation change here, a condenser is higher elevation than the others, that's going to be pretty minor in comparison to the other, the Q and the WS. Okay, so for this adiabatic expansion, we know that Q equals 0. And we also know there's no moving parts there either, so Q and WS are going to be 0. So for this one, delta H is going to equal 0. Okay, so across the evaporator, again, no moving parts there, WS equals 0. Okay, so we just have the Q, delta H equals Q of cold. Okay, and then up here in the condenser as well, no moving parts, delta H is going to equal Q hot. Okay, and then over here for our compressor, we could say there's not a lot of heat transfer going on there, so no Q, but we just have WS. So delta H equals negative WS. Okay, so this is going to be important because we're going to go down with constant here with H equals, delta H equals 0. Then we know that at the second state, at this 30 psia, I'm going to have the same enthalpy that I had before. So what I can do is I can just come down this line until I get to 30 psia. Okay, so there is my second point. Okay, so this was point 1, and this is going to be point 2. Okay, and that means I can look up some of these other things as well. Okay, so I have about let's see, what is it? About 27% vapor. Okay, and the rest is going to be liquid, and so I have liquid plus vapor. Okay, I'm in the two-phase region, and then if I look at the temperature as well, I'm about right here on the temperature lines. So it's going to boil at negative at 30 pounds per square inch. It's going to boil at about negative 12 degrees Fahrenheit. Okay, so there's negative 12. That's how cold this evaporator is going to be, that's removing the heat from the room or the refrigerator. It's going to be negative 12 degrees Fahrenheit. Okay, and then the H is going to be the same as it was before, because delta H was 0 for that adiabatic expansion through like a Joule-Thomson valve, for example. Okay, okay, and then we are going to evaporate this. So this is going to, we're going to extract the heat from whatever environment, an automobile, interior, a home, a refrigerator. We're going to extract that heat and let this boil. Okay, so we're going to go to saturated vapor. Okay, so it's going to be the same pressure, and so that means I'm just going to come over on this line until I reach saturated vapor, and that's going to be point number 3. So that so I'm at, I go 1, 2, 3. Now I need to get to 4. I need to get my fourth one. But let me go ahead and get the temperature here. This is going to be the same temperature. It's going to boil, and so that's going to be negative 12. but then I have a new enthalpy here. I added some Q, some heat, and so if I trace this down, then I get a new enthalpy of about 104. Okay, now the last one is going to be this compressor. Now if we say it's reversible, meaning it's the perfect compressor, has no losses in terms of entropy, then I can follow this constant entropy line as I increase the pressure up to, okay, so the pressure was 170, and I know that there's no change in pressure is over this, so isobaric. And so I need to get up to this 170 psi line. Okay, so it's going to be somewhere along this line, but I also know that I have to follow the constant entropy line. Okay, and so these are all the constant entropy lines that are going up, and if I come up to this point and I just trace that up, I'm going to hit my point number 4. Okay, so that's point number 4, and then I can get the enthalpy, the temperature, and the pressure. So that's going to be 170 on the pressure. The temperature, that is going to be 130 degrees Fahrenheit. Okay, so if we look, here's 140, here's 120, so it's just right in the middle of those two. So that's about 130 degrees Fahrenheit. And then if I trace down as well to get my enthalpy, then that's going to be 122 for my enthalpy. Okay, so we have the temperatures and pressures of each stream. We have the enthalpies of each stream. Now we want to get the mass flow rate that is circulating around here. Okay, no accumulation in any one vessel per se, and we're just going to assume steady state operation, although this compressor typically cycles on and off. We're just going to assume a constant mass flow rate around here. So about how much mass flow rate has to come around here. Okay, so the way we're going to do that then is, okay, so we're just going to start with, from the evaporator, we'll find the mass flow rate. Okay, so we know that we need that much cooling right there, and we know that this delta H equals Q cold, but we also know that delta H is going to be the mass flow rate times the change in specific enthalpy. Okay, and so we have those specific enthalpies right here. I'm going to put a little hat over that for specific enthalpy. Okay, and that we know has to be equal to Q cold. Okay, so we know this and we know that. The only thing that we don't know is the mass flow rate. Okay, so we can do that calculation. Okay, so let's just make this zoom out here just a little bit. Okay, so so we'll go ahead and calculate the mass flow rate of how much is circulating around, and so that is going to be delta H. So I'll just write this out: m dot delta H equals Q cold. Okay, so m dot times, okay, now we got to look at the difference between 3 and 2. So that's going to be 104 minus 32, and that's BTUs per hour. Okay, equals, and then we had 60,000 BTUs per hour. Okay, so actually this was not per hour, that was per pound mass. Okay, So if we divide this over, then m dot is going to be 60,000 divided by 72. Okay, and that's BTUs per pound mass, and that's BTUs per hour. And so BTUs are going to cancel, and that's going to be pound mass over hour, and that's going to be 833 pound mass per hour. Okay, so that's the flow rate of this R22 coolant as it circulates around in order to be able to get that much cooling. That's how much you have to boil per hour in the evaporator. Okay, so from the compressor, let's go ahead and find the work required. Now we know how much has to go through there, so let's find out how much work we have to put into compressing this. Okay, so again, so let's go ahead and calculate the shaft work that's put into the fluid. Okay, so that is going to be, as we said before, delta H equals negative WS. Delta H equals negative WS, but delta H equals m dot times, okay, now let's look at our difference. It's going to be the specific enthalpy of 4 minus the specific enthalpy of 3. Okay, so the difference between those two right there. Okay, so that's going to be 1